Hi guys. So today I want to talk about Black-Scholes model, and Black-Scholes model is basically used to price European style call and put options on an asset where the asset is basically modeled as a geometric Brownian motion. Okay, so in our case, you're basically going to consider a stock, and the stock is going to be modeled as a geometric Brownian motion, and you want to find out the value of a European call option or a European put option on a stock. Okay, so from the previous lecture, we already know how we model a geometric Brownian motion. We said if stock basically follows a geometric Brownian motion, then we can write ds of t is equal to sigma s of t dw of t plus alpha s of t dt, right? And we said that alpha basically is instantaneous mean rate of return, and sigma basically is the volatility term. And in order for the stock price to be a geometric Brownian motion, alpha and sigma both need to be constant. Okay, so that basically is exactly what we talked about in the previous lecture. And this basically is the differential of the stock that follows the geometric Brownian motion. Okay, so in our model, basically stock is going to be modeled as a geometric Brownian motion. Now what we want to do, the central idea behind Black-Scholes model is that we basically want to replicate the European call or a put option by trading in the underlying stock and basically a money market account. Okay, so this basically is very similar to what we've already discussed when we were talking about the binomial model. Okay, so I'm hoping that most of you guys have already seen those lectures. In case you haven't, right now would be a good time to actually go and revise them because the theory then is going to become much clearer. Okay, so let's assume that we are at time t, and at time t we have some money with us given by x of t. Okay, and at time t what we're going to do is we're going to basically buy a certain amount of stock, and the number of stock that we're going to buy is going to be given by delta t. Okay, this basically is the position in our stock. So if you basically want to buy delta t number of shares of stock, the stock at time t is basically trading at s of t. So we need to shell out delta t st amount of money to buy stock, right? This is basically the amount of money that we're going to invest in stock. But we had xt amount of money with us. So how much money is remaining after we buy the stock? We're going to have xt minus delta t st amount of money left, which we're going to invest in a money market account. Okay. In this model, we basically are considering the money market account to pay us interest rate R, and this interest rate R is basically continuously compounded. So by continuous compounding, we mean that if you basically invest $1 at time 0, and we want to look at the value of a money market account at time t, the money market account is going to be worth e to the power of RT. Okay, that basically is called continuous compounding. So we basically are investing this much money in our money market account that basically gives us interest rate R, which is continuously compounded. Okay. Now we have these two positions that we basically take at time t, and we want to look at the change in the value of our portfolio for a small change in value of time. So basically, as time moves forward by dt, we want to look at what is a change in the value of a portfolio. The change in the value of the portfolio is going to be given by dx of t, and this change is going to be driven by the changes in these two positions, the stock position and the money market position. So if you basically are holding delta t amount of stock at time t, in small time dt, the stock will change by ds of t. Okay, this basically is the change in the value of the stock. We were holding delta t amount of stock. This basically is the change in the value of the portfolio because of our stock position. Okay, now ds of t we've already talked about is basically modeled as a geometric Brownian motion. Okay, So this basically is the change coming from our investment in stock. What is the change coming from the money that we've invested in the money market account? We basically had xt minus delta t st. Okay, now this money was invested in a money market account giving us continuously compounded interest rate r in a very small period of time dt. This can be written as r times dt. Okay, so this basically is the amount of money it's going to accrue in a small interval of time dt. Okay, so this basically is the change in the value of the portfolio coming from our investment then in the money market account. Okay, now we can simplify this further. Instead of ds of t, I can write down this. So we'll get dx of t is equal to delta t sigma st dwt plus alpha st dt plus we have this term right here, xt minus delta t st r times dt, right? This we can simplify further. This will become d delta t sigma st dwt plus alpha times delta t st dt plus x of t r dt minus delta t st r dt. Okay, so we can write this down as, we can write this term right here first. We can write this as r times x of t. This is equal to dx of t is equal to times dt. Then we can combine this term and this term. If you combine these two terms, that can be written as alpha minus r delta t st dt. Okay, and now we're left with this term, so let's write that down. Sigma delta t st dw of t. Okay, so this is basically change in the value of a portfolio. Now we can actually interpret all of these three terms. This basically, the first term right here, r times xt of dt, is basically we could think of it as, you know, risk-free return on the value of a portfolio. Okay, this basically, alpha minus r basically is the risk premium that we get by investing in stock. Okay, and sigma basically is a volatility term which is proportional to our investment in stock. Okay, because volatility basically will come from uncertain returns in our stock. So this basically captures that. Okay, this basically is the risk-free return, this is the risk premium, this is the volatility term, and that's proportional to our investment in stock. Okay, so this basically is the value of the change in the portfolio. Next, I would actually like to consider two more differentials. So now we would like to also calculate what is d of e to the power of minus rt s of t and d of e to the power of minus rt x of t. And we can do that by Ito's lemma that we've already learned. So let's do that. Okay, so first I would like to actually focus on this. Here we can actually write the function as function of t and x. Okay, the function of t and x is given by e to the power of minus rt times x. Okay, if this is the function, then this differential d of e to the power of minus rt times st can be written as d of f of t and st, right? F of t and st basically would be x replaced by st. That's exactly what we're going to get. Okay, now we have a function of two arguments, t and st. T basically is time, and basically it has a zero quadratic variation. St basically is modeled using geometric Brownian motion, and it has a non-zero quadratic variation. So we can find this differential using Ito's lemma. So let's do that. Let's basically figure out what are the partials ft of t and x is going to be given by minus r e to the power of minus rt times x. F of x t x is going to be given by e to the power of minus rt. F of xx is going to be equal to 0. Okay, since st basically is having a non-zero quadratic variation, we need to consider the first and the second order terms. T basically is time, which has 0 quadratic variations. We are only considering the first order terms. Okay, so we can write this as d e to the power of minus rt st. Then basically, according to Ito's lemma, becomes ft times dt, right? So minus r e to the power of minus rt. Instead of x, I'm going to write st dt. Okay, that's the first order term. I don't need to consider the second order term here. But now let's consider f of x, which is e to the power of minus rt, and dx. dx in this case is going to be ds of st plus, because the second order is basically partial is basically 0, so I'm going to write this as 0. Okay, now since our stock is modeled as a geometric grounded motion, we can simplify this further. We can write this as e to the power of minus rt st dt plus e to the power of minus rt. Instead ds of t, I'm going to write sigma st dw of t plus alpha st dt, right? Let's simplify this. Minus r e to the power of minus rt s of t dt plus sigma st e to the power of minus rt dwt plus alpha st minus rt dt. Let's combine these dt terms. We have alpha here, so this can be written as alpha minus r e to the power of minus rt st dt plus sigma of times st minus rt dw of t. Okay, this is d e to the power of minus rt s of t. So very simple. We just applied the Ito's lemma. We had a function of two arguments, t and st. One had a 0 quadratic variation, the other one had a non-zero quadratic variation. We know how to capture this. So we just solved for this, and this simplified to this particular differential right here. Okay, so we've calculated d e to the power of minus rt st. Next, let's calculate the differential of the discounted value of our value of the portfolio. Okay, so let's do that.